Hello, in this video we will talk about using R to do t-test, or called students t-test. So students t-test is for the small sample, usually under the sample size 30, and the population is at least approximately normally distributed. So if we want to test the population mean against a specific value, so we can get a test statistic from sample. So this is the sample mean, sample average, then minus the value we want to test for the population mean. Then we divide it by standard deviation or standard error from the sample and divide it by the square root of sample size. So this is the sample variance calculation. Just note here we use n-1 in the denominator because the average of the sample calculation will lose 1 degrees of freedom. So we get this test statistic and we'll compare it with the critical value for the hypothesis testing with the critical value, or we compare with the p-value from this test statistic with the alpha, which is, for example, 0.05. We have defined in hypothesis testing for the very small probability returning the first type 1 error. And this is the t-distribution. So we can see if the degrees of freedom will be very small, the probability density curve for the t-distribution will be relatively flat. And if the degrees of freedom will be very large, we say over 30 at least, so the curve will be very close to a normal distribution. So that's why in hypothesis testing for the population mean, if the sample size is relatively large and we can say that the sample comes from at least a normally distributed population, so we can use the normal distribution for tests. So in a small sample size, usually we use a t-test, and t-distribution has a parameter for degrees of freedom. So this is the t-distribution, and from this table we can get either the critical value for the t, or we can get the p-value from the given critical value or given t-value. So this is the alpha associated with the t-value. So we call it t-alpha. So for example, alpha 0.05 for the 10 degrees of freedom. So this value is 1.812. So which means about 95% of the values in this t distribution will less than this value, right? So in the t-test, if we get the statistic from the sample from the previous page, we get a larger value than this value, then we will reject the hypothesis that the population comes from this given value, right? I would say the real population will be significantly different from this hypothesis tested value. And if we want to use t-distribution or do t-test, we have to know these functions for the t-distribution in R. So this is D for the probability density, and P for the cumulative probability, and Q for the quantile. So cumulative probability, which is same to say that we will get the white area under this probability density curve from a given t-value, right? And for the Q means quantile function. This is the opposite operation of P function. For the Q function, Qt, which means we know this white area's probability, then we try to calculate this T value. So this is the Q function is doing. And R for the random number generation. So these four functions will be the basics for the t-distribution in R. So next we go to RStudio to show how to use these functions and do a t-test. So first, we will create a sequence of vector of values from 0 to 10 by the step 0.2. Then we set a degrees of freedom 10. Then we can use dt to calculate the probability density for each value of this vector with degrees of freedom. And we plot with these values in x values in axis x and probability density in the y axis. So this is this t-distribution's probability density curve. So under this curve, the area will be 1. And for example, for t value 0 to 10, this is 1, right? The probability density is about 0.25. And next we will use same x values to create the cumulative probability for each value, and we plot in the figure. So you can see the cumulative probability using P function is increasing. So for example, 1 here is about 0.80. So which means about 80% of the values from this t-distribution will less than 1, right? And next function is Q. For the Q, we will input a series of probability, which means the cumulative probability. So we create a sequence of the vector of probability between 0 and 1, and degrees of freedom is 5. So we can calculate odd quantile value or odd t value associated with these probabilities or the cumulative probabilities. Then we plot in the figure. So you can see this is the quantile value. So here is the probability between 0 and 1. And this is the quantile value for t-distribution with 5 degrees of freedom. So you can see, for example, 0.7 here, the value is about little lower than 1, for example 0.9. So which means about 70% of the values in this distribution were less than 0.9, right? And for the R function, we can generate random numbers from a t-distribution. We generate 10,000 such random numbers from a t-distribution with degrees of freedom 10. And we plot in histogram. So this will mimic a t-distribution's probability density function. So this is the histogram or frequency counts for different values from a t-distribution. So you can see when the values less than 4 or the larger than less than minus 4 or larger than 4, and their counts will at least 0, almost 0, right? So now we will take a look at an example using t-test. So chemical engineer claims that the population mean yield of a certain batch process is 500 grams per milliliter of raw material. To check this claim, he samples 25 batches each month, and if the computed t-value falls between minus t0.05 and t0.05, he is satisfied with this claim. So what conclusion should be drawn from a sample that has a mean x bar equals 518 grams per milliliter and a sample standard deviation s equals 40 grams? So assumes the distribution of ES to be approximately normal. So here we can see that 25 is relatively smaller than 30, so we cannot use normally distributed or normal tests. So we have to use t-tests because we assume that samples come from a population which is approximately normal. And if we look at these tests, so this is a sample statistic, and this is the population mean we want to test against, and we assume this is correct in the null hypothesis. Then we get samples and test if we can reject this null hypothesis. So here the mu for the population is 500, right? And we get x bar for the sample, and we have standard deviation or standard error from the sample, right? So we get everything. Then calculating the test statistic. So first, we will calculate the critical value of t 0.05. So which means because we here get a two-tail test. So if the t statistic from the sample lies in this area or lies in the other side of the small probability area, in either of case we will reject the null hypothesis, right? So first we will calculate the critical value for 0.05 probability on the right. So we can use quantile function. So qt1 minus 0.05. So because the blue area is 0.05, so which means the white area is 0.95. So we use qt1 minus 0.05 and 24 degrees of freedom, because the sample size is 25, right? 25. Batches. So we can get to the t critical value. Here is 1.71. Then we calculate the sample statistic, which equals 518 minus 500, then divided by the standard error of the sample, divided by the square root of sample size. So this value is 2.25. So here you can see that 2.25 is much larger than this critical value 1.71. So we can reject the null hypothesis. Or you can calculate the p-value of this associated with this t-sample statistic. So we can use 1 minus pt, because the pt is for the cumulative probability, which is the white area. So we use 1 minus this white area, can return the p-value, right? The p-value is about 0.169. So this is also significantly smaller than alpha level. Alpha is 0.05. So we can also reject this null hypothesis that the population mean value is 500. We say that actually the mean value is much larger than 500 from this t-test, right? Thanks for watching.